5.2, number 72. So in this problem, they're telling us to evaluate the integrals of these functions using formulas for areas of triangles and circles and subtracting the areas below the x-axis. There's some fundamental things here. 1. Any area that appears below the x-axis, the integral will calculate as being negative. Okay? So this triangular region here is a negative value. Now, by the time it combines with these other ones, it looks like the overall areas all combined will be positive because there's greater area above than there is below. It's something always to keep in mind with integrals, how they work. Secondarily, you can just add area to area to area because of the last property that was illustrated in the previous part of the introduction. Okay? That's really what that's saying. So the entire integral from 0 to 12 is the same as the integral from 0 to 2 plus the integral from 2 to 6 plus the integral from 6 to 12. So you can always take disparate areas and just add them together to get the entirety of your integral. All right, the other thing is, when you have regular shapes that you have formulas for already in standard geometry textbooks, you are able to use them to compute integrals, right? Matter of fact, the integral of this here would be very difficult to compute through limits. Very difficult, very challenging. This one, not so much. But this one also very challenging because it's a semicircle. Okay? And all this complicated notation here is simply to describe the radius of this semicircle along with its center. Okay? So you don't need to worry about this expression so much for these problems. It's really just noting that the radius of the first semicircle is 1, right? If you have to verify that, you can simply plug the value 1 in here, plug the center value in of 1, and for x, you get 2 minus 1 is 1, the square root of 1 is 1, that's the height there, right? So there's the height of the semicircle, there's its radius. So its area is going to be pi r squared, of course. So pi r squared for first semicircle will be pi 1 squared is pi. So that's the area of the first semicircle. Once we cut it in half, of course. Okay? Because it's only half a circle, we'll just cut it in half, and we have our answer. So pi on 2 is that area. Over here for the triangle, we need to use the formula of the triangle. So 1/2 base height. What's the base? Well, the base looks like it's 1, 2, 3, 4 units, right? 6 minus 2 is 4. So we have 1/2 4 times the height. The height looks like a -2. Again, if you weren't sure, you could take this value here of 4 and plug it in. 4 minus 4 is 0. Magnitude of 0 is 0. Minus 2 is -2. Now, the height being -2 here, if you think about it in terms of negatives, already takes care of the fact that this area is negative. Right? So we get a -4 value here. That's the area of the triangle. Right? If I just called it 2 for the height, because I'm not thinking about it in terms of its location from x-axis, then I just need to realize that the area is below the x-axis, and I should just automatically make it negative whenever I get its value, or its magnitude. Okay, so we have 2 areas so far. Now the third one, again, all this complicated mess is telling us is that if I plug in the number 9 here, it'll map up to a height of 3, it looks like, right? You can plug it in just to make sure. 9 times 18 minus 9 times 9 is, of course, what, 81. So 81 minus 72 is 9. Square root of 9 is 3. Yes, the height is 3 here. Since the height is 3, we know that, again, pi r squared will turn out to be pi 3 squared, which is 9 pi. But again, it's only a semicircle, so therefore it is just 9 pi on 2 for the area of the semicircle there, the larger one. But it's positive, right? So this is a positive area, negative area, and positive area. For all integrals, they always view it this way. So therefore, the integral of f of x dx, right? If this is all one complicated function here, it would be piecewise, of course, but it's one complicated function. From 0 to 12 is nothing other than the integral of this function from 0 to 2 dx plus the integral of this function from 2 to 6 dx plus the integral of this same function from 6 to 12 dx. Right? But we know each of these three separately. So again, this is what the last property was showing us, that I can break the integral up from 0 to 12 into separate intervals, subintervals, and add them together, and it'll be the same as the original integral all the way from 0 to 12. So now we have our answer given as pi on 2 minus 4 plus 9 pi on 2. 9 pi on 2 plus pi on 2 is 10 pi on 2 is 5 pi. So we get 5 pi minus 4 as our answer for the whole integral.